Hey guys, time to start talking about rate law, which is where math comes into these collisions and these reaction rates. So it's not too bad. So imagine we have the following reaction. We're turning A into B. So over time, what happens to brackets A and brackets B? And just to be really sure, what do the brackets represent? So answer both these questions with your neighbor right now. Pause the video, answer both these questions. So hopefully you remember the brackets just mean concentration. So the concentration of A, the concentration of B. And over time, as this reaction proceeds, we're turning A into B, so we're going to get less and less and less of A. So the concentration goes down, and the concentration of B gets greater and greater and greater and greater. So if you think about this as a graph, in most reactions, it kind of depends, but if A is turning into B, it's probably going to look something like this. It's definitely going to go downward anyway, but this exponential decay is not uncommon. So it goes down because it's going away. Which part is used to determine rate law? We're usually talking about initial rate. So this very beginning part here, that's what we're talking about when we're talking about rate laws. We're talking about the initial rate of the reaction. So this is kind of what we use rate laws for in words. We're going to use it to understand the rates of the reaction with respect to the concentrations of the reactants. So we're looking at the concentrations of the reactants and how that affects how fast this reaction is going to happen, because it will. There is also a rate law expression, which is a mathematical equation, and it's specific not only to those reactants, but also to the other conditions of the experiment, temperature, all these other things. So imagine we have a hypothetical reaction. We've got some quantity, this is a coefficient, of A, this is the compound, and some quantity, the coefficient of B, and it makes some products. We don't really care about the products. We don't care what products there are. The products aren't going to affect this. The concentration of the products aren't going to affect this. We want to know about the reaction rate. We need to know about the reactants. So the rate law can be expressed in a mathematical equation, like I said, and it looks like this. So we have the rate, which is the actual rate of the reaction. Usually this is in like molarity per second or some concentration per second or change in concentration per second. So that's what it says down here. Usually it's molarity per second. Then you've got K, and this is the rate constant. And it is specific to these reactants in these conditions. More on that later. This is just the concentration of A. Then M is the order of the reaction with respect to A. So we'll get to what that means in a minute. And then the concentration of B raised to the order of the reaction with respect to B. And we'll get to what that means. In certain equations, this M and this N come directly from A and B here. But that's only a specific time, and I'll let you know when that is. So if we're given the following data for a reaction, right, we've run this experiment 3 different times with different concentrations of A and B, and we got different rates that we can measure. We'll do an experiment similar to this in the lab where we'll see how fast a reaction happens. So with these data, we can answer a variety of questions. For example, how does doubling A, the concentration of A, affect the rate? And you can see right here, without messing with B, so B's locked up, it's still 0.100, so it's not changed. We just doubled A. What'd that do? Well, it appears to have doubled the rate, right? So we doubled the amount of A, and the reaction goes twice as fast. Not terribly surprising. We can calculate the value for M in the rate law. So right now we have this rate equals, here's our rate law, right? K, brackets A, M, brackets B, N. And so if we take this reaction and we divide it by itself basically, but we divide different trials. So let's take this trial divided by this trial. And I choose it that way because it's nice to have the big one on top. It makes more sense. Mathematically, it allows things to happen more quickly. So I've got 0.004, that's 4 times 10 to the negative third, right? Over 0.002 equals, so like I said, I'm dividing this whole reaction trial 2, I'm doing trial number 2 divided by trial number 1. And since these are the same reactants and the temperature is the same and all that, the K's are the same. So K over K times the concentration of A in this trial, which is 0.200, raised to the M, over 0.100 raised to the M, times 0.100 raised to the n times 0.100 raised to the n. So you can see right away a bunch of stuff is going to go away. So this cancels, that cancels, and we're left with basically 2, because this is going to be 2, equals, now I got 0.200 raised to the m over 0.100 raised to the m. Now this is just, I can undo this by, it's basically the reverse of what? The distributive. I think that's what that is. What's just factoring, right? We're factoring. So we can make this 0.200 over 0.100, that whole thing raised to the m. That's acceptable. That's math. And so that means it's 2 raised to the m. So 2 is equal to 2 raised to the m. So that means that m is equal to 1. So m is equal to 1. Now let's look at this second reactant, B, and see how it affects the rate. So we need 2 of A's that are the same. Those 2 are the same. And we double B here, so that's perfect. This is set up very nicely for us. They aren't always quite so nice. So how does doubling B affect the rate? If I double B and leave A the same, it looks like it goes up 4 times, right? So this is 4 times as large. So B seems to be a bigger deal. If I double B, I get it 4 times instead of just 2 times that I got with doubling A. Let's calculate the value for n, and we're going to do the exact same thing, only this time we're going to use these 2 reactions. We're going to do reaction number 3 divided by reaction number 2. So it's going to be 0.016 over 0.004 equals K over K, 0.2, and we know m now is 1, so we're just going to leave that 0.2. That's raised to the 1, raised to the 1. Times, and this is 0.200, I'm sorry, those should be hundreds, right? Raised to the n over 0.100 raised to the n. These all cancel, just like before. This is going to be 4, because 16 over 4 is 4. And now we've got basically 2 to the n, right? I kind of shortcutted some of that stuff, but it's the same as what we did before. It's just going to be 0.200 over 0.100, that whole quantity raised to the n, and that's 2, right? 0.200 over 0.100 is 2, so 2 to the n. So in this case, n equals 2. So now we know that the rate law is this, is the rate is equal to K times the concentration of A, and it's raised to the 1. You could put the 1 there, but you don't need to. And then concentration of B raised to the second. So that's our rate law. The order of the reaction with respect to A, so the order of the reaction is the exponent on the concentration of A. So it's first order. With respect to B, it's second order because they've got a 2 right there. And then it may ask you, what is the overall order? And all you do is add up all of the orders. So this is first, this is second. So it is a third order reaction. This is a third order reaction. So which concentration affects the rate more? I kind of already said this. We said doubling B makes the reaction 4 times as fast, and doubling A only makes it twice as fast. So it appears that B affects the rate much more dramatically than A does. So what happened to the rate if you cut A in half? What would happen if you cut B in half? Pause the video, answer those questions. So hopefully you were able to say, if I cut A in half and left B the same, then the rate is going to be cut in half, right? Because it's the same as doubling it, only the other way. And if I cut B in half and left A the same, it would be cut to a fourth. The reaction rate would be cut to a fourth. Again, B has a bigger impact. The concentration of B has a bigger impact on the rate of this reaction, on how fast it happens. So we have this rate law. We can find the value of K, the rate constant. We can find this. And all we have to do is plug in these other values up here. It doesn't matter which one you pick. I like this first one. It looks pretty easy because there's lots of 1s in there. So let's do that one. So we're going to just plug those values in for A, B, and for the rate, and we'll be able to solve for K because that's the only variable left. So 0.002 equals K times 0.100, and that's raised to the 1, so we can leave that alone, times 0.100 again, only this is our B, and that has a 2 on it with our rate law, right? So we're just got to solve for K here, and if we multiply this all out, we're going to get 0.1 squared is 0.01, 0.1 is 0.1, so we're going to get 0.001. So K times 0.001 equals 0.002. Divide both sides by 0.001. That means that K equals 2. So now we got all of this. We figured out every single thing. We figured out M, N, and K using these data up here. Now remember, the units of the rate are molarity per second. If the units of the rate are molarity per second, what are the units for K? And I'll tell you, depending on the order of the reaction, these are going to be different. K can have different units because it has to have whatever it takes to make it all jive. So I've got molarity per second. That's equal to the units of K, which I don't know, so I'm just going to put K. I've got molarity, because it's the concentration of A, and that's raised to the first. The concentration of B is molarity, and that's raised to the second. Okay, so this is going to be molarity cubed, K times molarity, whatever the units are for K, times the molarity cubed equals molarity per second. So if we divide both sides by molarity cubed, we get 1 over, because that molarity is going to be, right, one of those is going to cancel and make that 2. So we get 1 over molarity squared seconds. That's the units for K. So there's a little shortcut here. Instead of having to work that out algebraically every time, we can just use this shortcut. The units for K are always going to be 1 over molarity raised to the order minus 1. So remember, this was an overall third order reaction. So molarity squared, which is what we had, times seconds. So 1 over molarity squared times seconds for this reaction, for a third order reaction, for any third order reaction. How is K related to the rate? Look at the algebra. The rate is equal to K times concentrations raised to numbers, right? I'm just going to do A and B and N. As K goes up, the rate goes up. As K goes down, the rate goes down. They're directly related. That's all you need to know. So I've got a bunch of practice problems for you. So I want you to pause the video, do this problem, and it's got several parts. It's a lot like what we just did. So A through E. Then I want you to do this problem. It's a couple of different questions to make sure you kind of understand. So if I add H2O, what I'm affecting there is the concentrations, right? So think about the concentrations, how that's going to affect our rate, right? It's asking about the rate. It's also going to ask about K. If you heat this reaction, how's that going to affect the rate? You know how temperature and rate are related. Does that affect K? See if you can figure that out. And then part C, right? We're talking about sodium hydroxide, so we're going to cancel this stuff out. So think about what's going to happen here. Our hydroxide is going to react with our hydrogen, so we're going to be reducing the concentration of the hydrogen, right? Because we're neutralizing that and just making water. So think about how that's going to affect these questions. I want you to do this one. It's pretty straightforward. It's a little bit trickier because the numbers aren't as easy to work with, but see what you can do. So I want you to pause the video, work out all those practice problems down to this one, right? Finish this one, and then I'll go through them all. You can play the video again, and I'll just be going through solving these problems, okay? So you can check your work. Okay, hopefully you didn't have too many problems with this, but I'll walk you through just to be sure. So when we go to determine the rate law for this reaction, we want to do what we did before. We're going to see here that we are keeping this nitric oxide concentration the same, but we're doubling the H2, and when we do that, it appears to double the rate. And so we know that that's first order reaction, right? When it doubles, that's a first order reaction. And if you look at this second one here, we're going to double this, but we need to look at this one and this one, not this one. So we need to actually look at these. We're going to look at the first and the third, not the second and the third. And from that, you find that when you double the nitric oxide, you quadruple the reaction rate. So that makes it second order. So the rate law is rate equals K times the concentration of NO, and that was the one we just said was second order, concentration of H2, and that was first order. So I'm just going to leave it like that. Still looking at the same reaction. The order with respect to NO, well, that was second order. The order with respect to H2 is first order. The overall order of the reaction is third order, right? Because you just add them together. We can calculate the rate constant pretty easily too. I'm going to pick this first reaction again because I like those concentrations. So we're going to do the rate, which is 0.00123 equals K times 0.1 to the second times 0.1 for the hydrogen, right? So this is going to be 0.001 times K equals 0.00123. So we're going to divide both sides by 0.001. So that's the same as multiplying both sides by 1,000. So 1, 2, 3. We're going to get 1.23 equals K. And if I screwed something up, because I do kind of blast through these, if I screw something up, shoot me an email and I'll post a correction. Last year, I would give imaginary Smarties to anybody who corrected an error in my presentation. So you will get imaginary Smarties if you find an error and you're the first to email me the correction. So the units for K, remember we have that shortcut. It's 1 over the molarity to the order minus 1. So this is the overall order was 3. So molarity squared times seconds. So that's the units for K. Pretty straightforward as far as that goes. And calculate the rate when. So let's find the rate. So we know now what K is. K is 1.23. We're trying to find the rate times 0.050 squared times 0.150. And again, I did not bring home my calculator. I got to do it with my freaking phone. So when I calculate all this out, I get 4. Looks like we've only got 2 sig figs. So 4.6 times 10 to the negative 4th. And the units are going to be molarity per second. So that's my answer. So when given these concentrations and all the conditions are the same as what we used for this, temperature, etc., this is our rate. This is how fast the reaction happens. Okay, moving on to the next problem. Consider a solution with blah, 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 blah. So this one is not so mathy. It's just kind of, do you understand the math? And this is the kind of thing AP likes to ask about. So let's see what's going to happen here. If I add water to this solution, right, I am decreasing both of these values. So what's that going to do to the rate? The rate's going to go down, right? Because these numbers go down, the rate has to go down. Does K increase or decrease to stay the same? Concentration has nothing to do with K, right? K is everything except the concentration, right? Because the only thing in this equation that affects the rate is the concentration and K, right? Hopefully you can see that. So we're looking at the rate of the reaction, how fast the reaction happens. This rate law gives us two things: the concentration of the reactants, how that affects the rate, and then K, how that affects the rate. So think about all the other things we talked about, right? There's a lot of things that can affect the rate of the reaction, but the ones that are not concentration, those are all built into K. So K is not changing because all we did here was change the concentration. So K stays the same. Only change the concentration. We look at part B here, we're heating it. So now we're changing K, right? Because we're not changing the concentration. The concentration is exactly the same, but the rate is definitely going to increase. We know that heating a reaction makes it react more quickly. Right? That's always the case because particles are moving faster, more collisions. The collisions have more energy. All of that is going to make it so that we have a faster reaction rate. Think about everything we did in that first introduction to kinetics. So K is going to be larger because that's going to make the rate larger. K is going to increase. The rate increases because the temperature increased. That increase caused a change in K, and that's why the rate value increases. So we're going to add sodium hydroxide. Now, sodium hydroxide is going to cause a separate reaction. Hydroxide ions, this guy, OH minus, which this is going to ionize right away into sodium ions and hydroxide ions. We don't care about the sodium ions. They're not going to do anything. But these hydroxide ions are going to react with the H+, and they're going to make water. And so that decreases the concentration of this. So does the rate increase or decrease? It's going to decrease because we have less H plus. Does K increase, decrease, stay the same? K does not change. We're only messing with concentrations here. So K stays the same. So looking at these data, we got to figure out what's the rate law for the reaction. So there's a bit of a curveball in here. Look at how the rate is unchanged when we increase the concentration of A. So this is a little weird because we didn't talk about this. So if the initial concentration, that's all this little O means, by the way. Don't get fooled by that. That little O just means initial, originally, at the beginning, at 0. So if I have an increased concentration, B is locked down, staying the same in both of these, but A is 0.5, A is 0.75, but the rate remains unchanged. That's a little bit weird, right? This is what we call a zero order reaction. And so a zero order reaction, you can think of the rate law as being, right? So it would be rate equals K times the concentration of A raised to the 0 times the concentration of B raised to whatever n is. And we'll do that here in a second. But you can see A raised to the 0, of course, any number raised to the 0 is 1. So I can get rid of this whole thing. Right? So the concentration of A doesn't really affect this at all. That's called a zero order with respect to A. And we'll come back to that in a second. So that's a bit of a weird one. That probably stalled you in your ability to solve this problem. So pause the video again and see if you can complete it now that I've given you that little key. So we know that A is not a factor. We're still coming up with this rate law, and the rate is going to be equal to K, no longer have A in there, B raised to the n. Well, let's find out what n is. We could choose 1 and 3, or we could choose 2 and 3. It doesn't really matter. We need to see what happens, though, when we double B. And you can see it doesn't matter how, no matter what you do, because, again, A doesn't matter anymore because that's zero ordered. So whenever we double B, the same result happens. We double the rate. And so that means it's B to the first. It's first order, right? If it quadrupled, it would be to the second order, but it doesn't quadruple, it just doubles. So you double the concentration of B, you double the rate, that's first order. So this is our rate law, we're done. This is it, that's the whole thing. The overall order of the reaction is first order. This is a first order reaction, 0 for the A and 1 for the B. What's the value for K? Well, that should be easy to solve. Let's find that. The rate is equal to, which one should we pick? Let's just pick the first one. 0.050 equals K times 0.20. So K equals 0.050 divided by 0.20. So hopefully you can see that that's just 1/4, right? 0.05. So 5 over 20 is 1/4. So 0.25 is K. When you go to find the units for K, which it doesn't ask you to do that, but you could easily do it. Remember, it's just 1 over the molarity raised to the order minus 1. Well, it's a first order reaction, so it's the molarity raised to the 0, so that's 1. So it's just 1 over seconds. So that's our value and units of K. Is that a little harder than what AP would ask you? Yeah, probably. But if you can go farther, then it makes the AP seem easier. So that's what we're doing. And this isn't that bad. So I want to talk about the zero order, make sure you got this down. The only time this is going to happen is if you have a whole lot of that stuff. Like the concentration is there in such abundance that it is always available every single time this reaction is happening. So it doesn't affect the rate because it's always there. That's the only time you're going to get a zero order reaction. They are kind of weird and uncommon. But be aware that they exist because it will come up. So basically it's like the concentration just doesn't even change. It's so constant. There's so much of it that taking a little bit doesn't do anything, right? It's still so much of it there. So that's kind of an intro to the rate law stuff, including a couple of little tweaks, a little curveballs, little things you might encounter. Shouldn't be too bad. We'll practice this a little bit more probably, and we'll be ready to handle that. So we'll go on from here. And the next one, we'll do integrated rate laws. We'll look at complex reactions and how to identify the rate limiting step. And how to get rate laws from that. So shouldn't be too bad. I know this isn't ideal, but you guys are doing great. Hang in there. Email me questions.